who is a PhD student at IISc Bangalore. His talk is positivity preservers forbidden to operate on diagonal blocks. Okay, over to you, Vishwakarma. Welcome.
Thank you, ma'am. Hello, everyone. Before we begin, I would like to thank the organizers for conducting this meet and letting me speak here. In this talk, we discuss about the classification of functions that act on matrices in the enterprise fashion and preserve the cone of positive semi-definite matrices. Positive semi-definite matrices are Hermitian matrices which have non-negative eigenvalue, or equivalently that the corresponding quadratic form is non-negative over Cn. This directly implies that the class of positive semi-definite matrices is a closed convex cone, meaning that the class is closed under pointwise limit, summation, and positive scalar multiplication. In this talk, we focus on the class of PSD matrices which have entries in the interval minus rho or rho positive or infinity, and the entry-wise functions that preserve the positivity of this class. We use the notation Pn to denote the class of all n by n PSD matrices, and Pn of I to denote the class of all n by n PSD matrices which have entries in the set I. So the search for entry-wise positivity preservers began with the discovery of the Schur product theorem, which states that the entry-wise product of positive semi-definite matrices is again positive semi-definite. For instance, this implies that the k-fold entry-wise product of a positive semi-definite matrix, as shown in the picture, is again positive semi-definite. This implies that the monomials, when act on entry-wise on any positive semi-definite matrix, yields positive semi-definite matrix. This, along with the fact that the class of PSD matrices is a closed convex cone, any convergent power series with non-negative coefficient is again an entry-wise positivity preserver. Such power series are also known as absolutely monotonic functions. It was not very long after Polya and Zigo that Schoenberg proved that there are no continuous, non-absolutely monotonic entry-wise positivity preservers. This result of Schoenberg was later improved by Rudin, in which he removed the continuity assumption of Schoenberg and showed that the class of entry-wise positivity preservers coincide with the class of absolutely monotonic functions. This Schoenberg-Rudin theorem is gaining recent attention due to its applicability in modern analysis. And in one of those applications, it was necessary to understand the classification of entry-wise positivity preservers which acted on off-diagonal entries. This classification was obtained by Gu and Rajaratnam in 2015, in which it showed that such entry-wise positivity preservers are those absolutely monotonic functions which are bounded above by the modulus function. To summarize, in the beginning, we saw the entry-wise positivity preservers which acted on all the entries of the matrices, and that they are all absolutely monotonic. Then we saw the entry-wise positivity preservers which acted on off-diagonal entries, and that they are also absolutely monotonic. In this work, we have generalized to the idea where the function f is operating on generalized off-diagonal entries, in the sense, for instance, as shown in the picture, where the function f is forbidden to operate on the first principal 2 by 2 block, but is acting on A33 and so on. We have pushed this idea one step further, where the function f, where a given different function g is operating on the entries where the function f is not operating. More precisely, if suppose Tn is a subset of power set of bracket n, where bracket n is the set of integers 1 through n, then in the operation g of Tn, function g operates on the principal blocks which are indexed by the sets sitting inside Tn, and the function f operates on the rest of the entries. For instance, if T3 is the set containing 1, 3, and 2, then in the operation g of T3, function g operates on operates on principal blocks indexed by 1, 3, and 2, and the function f operates on the rest of the entries. Similarly, when T4 is the set containing 1, 2, 3, 2, 4, then the operation g of T4 looks like as shown in the picture. Note that in T4, there are sets that are intersecting with each other. We allow such intersections in our set of results. Now, the question that we ask here is of the classification of the functions g and f such that the operation g of tn preserves positivity over pn of I for all n given any sequence tn. Observe that the question here allows us to assume that there are no comparable sets sitting inside any of the tn's, because the smaller set would be redundant. Because of the time constraint, I would like to stick to the case where g is the identity function from now on. Please have a look at the paper for more refinements. Note that when Tn is the empty set, the function f operates on all of the entries, and which leads us to the Schoenberg-Rudin theorem. And when Tn is the set of singleton subsets, set of all the singleton subsets of set bracket n, the function f operates on all the off-diagonal entries, which leads us to the Giu-Rajaratnam's result. And in both of these cases, as we have seen, that the preservers are absolutely monotonic. Now, to look at the new preservers where Tn's are different than these two cases, we look at this result. Now, suppose f is a real function on the interval I, where I is the interval -ρ for rho positive or infinity, and Tn is the subset, and Tn is a given sequence for which each Tn is a subset of power set of bracket n, such that none of the Tn's contain the set bracket n itself. This extra assumption on Tn is there to make sure that the function f is operating on arbitrarily large matrices, essentially to make sure that the classification that we obtain is of dimension-free character, is dimension-free. Now, under this setting, the following are equivalent. That is, the operation ftn preserves positivity over pn of I for all n, if and only if the function follows the following characterization. Now, the characterization here depends on the sequence Tn. So for instance, in the first case, if in the sequence each Tn is the empty set, that is, the function f operates on all the entries, as we have seen in the Schoenberg-Rudin theorem, that the function f has to be absolutely monotonic. In the second case, where the function f is forbidden from some only from some diagonal entry of large enough PSD matrices, and in which case, as we have found, that the function f has to be absolutely monotonic and has to be bounded above by the identity function over the non-negative side of the interval. Note that a particular case of this, in this case, leads us to the Giu-Rajaratnam's result. Now we move on to the third case, in which the function f is forbidden to operate on at least one 2x2 principal block, in which case, as we have found, that the preservers are all linear functions, which vanishes at the origin, and where the coefficient c could be negative if each of the Tn is the partition of set bracket n, and the number of parts in Tn is uniformly bounded. Note that this is the case which yields us the first non-absolutely monotonic entry-wise dimension-free preserver. Now, for the remaining subcases of C, the coefficient C has to belong to the closed interval 0 to 1. And finally, for the case where the function f is forbidden to operate on at least two intersecting principal blocks, the preserver's f has to coincide with the identity function in this case. Now we have seen that with having seen this classification, we observe that this classification has brought the classical result of Schoenberg-Rudin and the modern result of Giu-Rajaratnam under the same frame of work. This classification has also yielded first examples of dimension-free, non-absolutely monotonic entry-wise positivity preservers. Since the search for such entry-wise positivity preservers began with the observation of Pauli and Zigo, this work has also increased the richness of the preserver problem by introducing the notion of two function GF preserving positivity. And the initial classification done along this direction follows us to a problem which could improve upon the work done on the critical exponent of graphs. Here are the references. Thank you. I'll stop here for questions.
Thank you for this very really liked it. Are there any questions from the audience? No question? Okay, in that case, let's thank the speaker once again. Thank you.
Ma'am.
Thank you very much. Yeah.